thoughtful speeds, micro details/visuals to hit the plus 15 to 35% target. $90 billion represents the annual valuation of the global industrial fastener empire. Within this massive market, the most critical components are the oversized bolts and nuts that provide the structural integrity for the world's entire industrial infrastructure. Why is such a massive financial investment directed toward these specific steel parts? One might assume they are merely basic metal rods with grooves, but without the integration of advanced metallurgy and high-pressure forging, these components would shear under the immense vibrational and gravitational loads of bridges and skyscrapers. It only looks obvious that a bolt is a simple piece of machined steel. In reality, each unit is the calculated end product of a multi-stage sequence involving thermal processing and rigorous mechanical verification. The process is only gaining momentum as the raw material enters the first stage of transformation. One can notice how the cylindrical steel stock moves toward the high-pressure forging station with a rhythmic mechanical clank. The equipment gradually compresses the metal, shaping the characteristic hexagonal head with thousands of tons of force. A single minor deviation in the molecular quality of the material, or a microscopic flaw in the thread geometry, renders the entire joint structurally compromised. It gets more complex further on. Heat treatment remains a mandatory phase where the internal grain structure of the forged steel is permanently altered to reach peak hardness. One can notice the faint orange glow of the metal as it emerges from the hardening furnaces before being plunged into controlled cooling baths. This thermal cycle ensures the bolt can withstand the specified tightening forces without stretching or fracturing. Every batch undergoes a series of strictly regulated mechanical tests to confirm that the physical properties match the engineering requirements. The camera glides along the laboratory sensors, where hydraulic presses apply extreme tension to the finished fasteners until the point of failure is recorded. The equipment precisely measures the exact moment the steel yields, ensuring that no substandard part reaches the construction site. Raw steel is thus systematically transformed into the mechanical foundation that supports the modern built environment. Everything only gets more complicated as the finished bolts are sorted and prepared for their final application in heavy industry. The molten and forged elements have reached their final equilibrium, standing ready to secure the massive structures of the world. Thus, the steel reaches the standard ready for the further stage. 150 millimeters. This is the diameter of the high-strength alloy steel bars that serve as the foundation for industrial fasteners. The production of large-size bolts and nuts begins with the mechanical separation of these massive round bars into individual billets. Automated cutting systems receive the raw steel, where hydraulic shears or high-power industrial saws divide the material into segments of strictly defined length and mass. These machines produce square, flat cuts that maintain the integrity of the internal grain structure without causing deformation. One can notice how a steady stream of coolant is sprayed directly onto the cutting interface to suppress thermal energy and flush away microscopic metal chips. This constant lubrication stabilizes the tool and ensures the billet surfaces remain free from heat-induced damage. Why are bolt billets cut significantly longer than those intended for nuts? At first glance, the two components seem similar in scale, but the bolt requires a much larger volume of raw material. This extra length is necessary to provide enough steel for the forging of both the extended load-bearing shank and the hexagonal head. A single industrial shift allows a machine to process thousands of these individual units with high efficiency. Each individual cut is completed in just a few seconds, yet the precision remains absolute. Even a minor deviation in the initial dimensions would compromise the mechanical strength and final geometry of the finished fastener. 2,100 degrees Fahrenheit. This is the peak temperature required to prepare the steel for the next stage of transformation. While both components move to the heating phase, the application of thermal energy differs fundamentally between the two. For nuts, the entire cylindrical billet enters a continuous furnace to undergo uniform heating across its entire volume. This full-body thermal treatment brings the metal to a completely plastic and homogeneous state, allowing it to flow evenly within the forging die. It is visible how the glowing steel reaches a state where a solid hexagonal body can be formed before any internal drilling or threading occurs. This is not the limit. The temperature is monitored with extreme extreme rigor to prevent surface oxidation while keeping the core soft enough for the high-pressure molding process. Bolts undergo a specialized thermal treatment that targets only a specific section of the material. Instead of heating the entire bar, an induction system focuses energy solely on the head portion of the billet. Within a span of a few seconds, the front end of the steel begins to glow a bright orange red, signaling it has reached the ideal forging temperature. Meanwhile, the shank located behind the heated zone remains significantly cooler and maintains its original rigidity. This localized heating method concentrates the energy exactly where the hexagonal head will be shaped, which significantly reduces total power consumption. At the same time, it preserves the metallurgical properties of the shank, which serves as the primary load-bearing segment of the bolt. One can notice the speed at which the heated billets are transferred into the hot forging station for immediate shaping. For the production of nuts, the uniformly heated steel is placed inside a closed die, where a high-capacity hydraulic press exerts immense force. The metal is compelled to flow into the hexagonal mold, compacting the material and rearranging the crystal grains into a much tighter and denser configuration. During every compression cycle, the internal surfaces of the die are sprayed with a specialized high-temperature lubricant and coolant. This fluid barrier protects the equipment from the intense heat and reduces the friction generated during continuous operation. Everything only gets more complicated as the metal takes its final structural form. It seems simple to shape a bolt head, but the precision required during induction forging is substantial. The billet is aligned so that the glowing hot end sits perfectly within the forging die, at which point the press applies vertical force to spread the metal outward. This creates the characteristic hexagonal head while the die is simultaneously coated with a protective layer of high-temperature lubricant. When this liquid makes contact with the hot metal, it evaporates instantly, creating a temporary gaseous film that prevents the steel from sticking to the mold. This ensures that every bolt head emerges with sharp, well-defined edges and a clean surface finish. The process does not end at this stage. 60 minutes is the duration often required for these large-scale components to reach a stable temperature after leaving the press. Once the forging is complete, the red-hot bolts and nuts are discharged into large steel containers to undergo natural cooling in the open air. For the largest industrial fasteners, this duration can extend even further depending on the total mass of the steel. This gradual cooling strategy is critical for preventing thermal shock and minimizing the risk of microscopic stress fractures within the metal. By allowing the heat to dissipate slowly, the internal structure of the part remains stable and the overall shape is preserved before the components move to the cleaning area. Why must the forged parts undergo a rigorous surface cleaning process? To the naked eye, the cooled parts look ready, but they are covered in a layer of dark oxide scale from the high-temperature forging. The components are loaded in bulk into large rotating drums or vibrating barrel machines that tumble the parts together. As the drum rotates slowly and steadily, the constant mechanical friction between the pieces scours the surfaces clean. This tumbling action also serves to sharpen the hexagonal edges and ensures the metal is dry and uniform across the entire batch. In a large-scale facility, hundreds or even thousands of parts are cleaned simultaneously in a single cycle. 10 to 30 minutes of continuous tumbling is usually sufficient to remove all traces of burnt scale and oxidation. The specific duration depends on the size of the fasteners and the thickness of the oxide layer formed during the heating stages. When the cleaning cycle concludes, the parts are discharged with a bright metallic finish that is free of impurities. This preparation is essential because it improves the dimensional accuracy of the parts and prevents premature wear on the precision tools used in the subsequent machining steps. Transition to the next level. The clean parts are now ready for the application of their permanent industrial identity. One can notice the mechanical stamps being pressed into the surface of the metal during the identification stage. For nuts, these markings are placed directly onto one of the flat hexagonal faces, while for bolts, the symbols are stamped onto the top of the head. These identifiers provide a technical record of the strength grade, the manufacturing standards followed, and the origin of the part. These markings serve as a mandatory identity card that allows the fasteners to be used in critical infrastructure, such as heavy machinery and large-scale construction projects. Without these verified stamps, the parts cannot be approved for industrial application. It only looks obvious that the threads are the most important feature, but their creation requires the highest level of machining precision. The bolt threading process begins with a light finish turning on a lathe to ensure the shank has a perfectly exact diameter and a smooth surface. The bolt is clamped securely and rotated at a high stable speed while a cutting tool skims the exterior to correct any minor imperfections. After this preparation, the part moves to a thread rolling machine. In this stage, the shank passes between two hardened rollers that contain the thread profile. The metal is not cut, but rather plastically deformed and forced to rise into the shape of the threads. 3 seconds is all it takes for the smooth shank to be transformed into a system of sharp, uniform threads. This rolling method creates a much stronger thread than traditional cutting because the grain flow of the steel remains continuous. For nuts, the internal threads are created using high-power tapping machines that rotate a threaded tool through the central hole. The tap advances steadily, carving the helical profile that must perfectly match the external threads of the corresponding bolt. The nut remains fixed in a heavy clamp to ensure that the threads are perfectly concentric and consistent in depth. The process is only gaining momentum. One can notice the continuous flow of specialized lubricating fluid saturating the machining zone during the entire threading operation. For bolts, this fluid minimizes the friction between the rolling dies and the steel, ensuring the surface finish remains flawless. In the case of nuts, the liquid serves the dual purpose of cooling the high-speed tap and flushing away the steel chips generated by the cutting action. This controlled thermal environment allows both the internal and external threads to achieve a high degree of dimensional accuracy. Once the machining is finished, the parts are fully prepared for the final verification of their mechanical properties. Why is the quality inspection stage considered the most critical part of the entire production line? A single failure in a structural fastener could lead to the collapse of a massive industrial system. The inspection begins with geometric verification, where experts check the diameter, thread pitch, and the sharpness of the profile using calibrated gauges. Every thread must fit perfectly with the standard instruments, as even a microscopic deviation results in the immediate rejection of the part. Following the physical measurements, the components undergo mechanical testing for surface hardness, tensile strength, and resistance to torque. The material is finally ready to transition from a semi-finished part into a complete structural component. Only those batches that pass every rigorous test are moved to the final packaging area. From this point, the bolts and nuts are dispatched to various destinations, including power plants, steel bridges, and offshore drilling platforms. In these environments, each individual fastener will be responsible for maintaining the structural integrity of massive industrial complexes. Thus, the steel reaches the standard ready for the further stage of its life cycle in the world of heavy engineering. 65 to 67% is the iron concentration achieved after the initial journey of purification begins. Once the raw iron ore has been ground into a fine powder, it is blended with water to create a thick slurry that is directed into massive flotation cells. Why are surface active chemicals added with such precise control during this stage? The mixture seems ready for simple separation, but in reality, the reagents are the key to the entire chemical process. They render the iron-bearing particles hydrophobic, while silica, clay, and other unwanted impurities remain hydrophilic. This marks a critical turning point where unshaped stone is reborn as a refined resource, fully prepared for the demanding path of metallurgy ahead. Compressed air is continuously pumped from the bottom of the cells. Millions of microscopic bubbles rise through the liquid, attaching themselves to the chemically tagged iron particles. One can notice how the ore gathers into clusters, forming a thick, reddish-gray froth that floats to the surface. Everything only gets more complicated as the process gains momentum. The worthless gangue sinks steadily to the bottom, completely separated from the valuable material. This iron-rich froth is carefully skimmed off and collected through multiple cycles. It is visible how the equipment produces a concentrate with a metallic content more than twice that of the raw ore. After obtaining the concentrated ore from the flotation tanks, the next stage is filtration and dewatering. Vacuum filtration systems, typically drum or disc filters, receive the iron-rich slurry. Under the pull of pressure differentials, water is drawn out while the fine ore particles remain. This step significantly reduces the moisture content, forming a moist filter cake on the surface of the equipment. At first glance, the filter cake looks like simple mud, but in reality, this dehydration ensures the material is better prepared for pelletizing. The iron concentrate emerges as a fine, dry powder, red as dust from the filtration tanks. But this loose form is far too fragile to be fed directly into a furnace for melting. To solve this structural problem, the powder is mixed with a measured amount of water and binding agents. The process is only gaining momentum as the mixture is poured onto giant rotating discs tilted at a specific angle. With each steady turn of the machine, the tiny grains begin to roll and cling together. They grow in size and round out, transforming into small pellets with a distinct reddish-brown hue. One can notice how the formless powder becomes millions of fresh pellets, uniform uniform and spherical, yet still soft and delicate. These young pellets must endure further stages ahead to gain the strength and hardness required to withstand the fiery heart of steelmaking. Dozens of meters is the length of the colossal steel cylinder known as the rotary kiln. The glowing red pellets continue their journey from the great conveyor into this massive structure, which is set at a slight incline and turns slowly on its axis. Inside, flames shoot from the kiln's mouth, sweeping the entire length and turning the chamber into a blazing river of heat. It gets more complex further on as the thermal treatment begins. Pellets tumble and roll evenly through temperatures ranging from 1,200 to 1,350 degrees as the drum rotates. This constant motion ensures each pellet is baked uniformly from core to surface, eliminating weak spots or cracks. Impurities and residual dust are burned away, while the ore particles fuse together into a dense, solid structure. The equipment gradually transforms the fragile spheres into resilient pellets clad in a tough shell. 2,000 degrees is the temperature soaring inside the towering blast furnace, the beating heart of iron making. Once the iron ore has been pelletized or sintered, it joins forces with the blazing hot coke fresh from the ovens. Layers of ore, coke, and limestone are charged in sequence at the top of the furnace. A powerful blast of hot air is injected from the base to sustain the reaction. Transition to the next level of chemical reduction occurs here. The coke ignites fiercely, releasing carbon monoxide that strips oxygen from the ore. This reduces the solid material into streams of molten iron glowing red hot, but such industrial power comes at a price in the form of carbon dioxide emissions. Massive volumes of gas, fine dust, and noxious fumes escape from the furnace during the transformation. One can notice the scale of this step, which stands as one of the largest single sources of industrial pollution on the planet. Colossal steel vessels lined with refractory bricks receive the molten iron immediately after it leaves the blast furnace. Here, the raw metal undergoes a violent purification in the basic oxygen furnace. From above, a massive lance descends, blasting a jet of pure oxygen at tremendous speed onto the liquid surface. The oxygen ignites instantly, stripping away carbon and impurities while sending pillars of flame high from the furnace mouth. Every fraction of carbon is burned off amid the roar and blinding sparks. This process transforms brittle pig iron into steel that is cleaner, tougher, and infinitely more versatile. It is the very moment of rebirth when crude metal evolves into the foundation of modern infrastructure. But the steel cannot remain in its molten state for long. The process does not end at this stage. Liquid steel pours into water-cooled molds through continuous casting machines. The metal lays in an even layer as it solidifies into billets, slabs, or blooms. This marks the first tangible form of the finished product. From these semi-finished shapes, the journey of transformation continues toward the rolling mills. Thick slabs are stretched into thin sheets under rollers weighing dozens of tons. Blooms are drawn into massive coils, and square billets become long, slender bars as they pass through the machinery. With every roll and every press, the metal moves closer to its final destiny. One can notice the rhythmic movement of the steel as it takes the shape required for skyscrapers, bridges, or automobiles. The entire process concludes as a symphony of metal, from the searing oxygen furnace to the thunderous cadence of the rolling mills. The material is ready to move to the next processing phase without haste. Thus ends one of the key stages of steel production. 100% of the manufacturing journey for high-strength industrial fasteners is defined by a sequence of rigorous transformations that turn raw steel into precision components. Why is such an extensive series of stages necessary for a seemingly simple bolt? At first glance, the process might appear to be a basic reshaping of metal, but in reality, the structural integrity of the final product depends on the exact execution of every thermal and mechanical transition. The raw steel bars are first subjected to a high-speed billet cutting phase, where specialized saws divide the long beams into specific segments with a precision of 1/100th of an inch. The process is only gaining momentum. One can notice how the cold steel blocks are fed into induction furnaces where the heating stage begins. The metal stays in an even layer as it passes through the thermal zone until it reaches a glowing orange state, making it pliable for the high-pressure forging machinery. It is visible how the massive hydraulic presses descend with thousands of tons of force to compress the heated billets into the hexagonal heads of the bolts and and the bodies of the nuts. Everything only gets more complicated as the forged blanks move toward the thread machining department. Automated lathes and rolling dies rotate ceaselessly to carve or press the helical grooves into the hardened surface of the metal. It does not end at this stage, as every single unit must then pass through a multi-point inspection where laser micrometers and ultrasonic sensors verify the dimensions and internal density of the steel. The equipment gradually moves the approved components toward the final packaging lines. One can notice the systematic sorting of the finished hardware into heavy-duty containers designed for global transport. Thus, the steel reaches the standard ready for the further stage of industrial application without haste.